Atomic radius is a very interesting and critical concept. Now start it with a very simple scenario. Consider a football. If I ask you to calculate its size, it is quite easy. You can measure its circumference without any complication. And similarly, if I ask for measuring its atomic weight, it's again not a hard nut to crack. You can just put it at any physical or digital balance and calculate its weights. Why do we not feel any difficulty while measuring size and weight of the football? The answer is clear. Football is a distinctive object, and at macro level, we can easily measure both size and weights due to sharp visibility of the objects. But what about atoms? Atoms are micro objects. They are too smaller. Even ordinary microscope is unable to observe them. The compound microscope reveals that diameter of atom is around 10 raised power minus 10 meters. Now the problem is how to measure an object that is not even seen with the naked eyes. To address this challenge, we encounter Niels Bohr's atomic model. In 1913, Niels Bohr proposed flat model for atom in which electrons move around the nucleus in definite orbit known as shells. He stated shells are fixed and therefore he allocated different names to these shells like K, L, M, N, etc. This structure makes us able to measure the size of atom because it's look like circle, and by applying simple mathematical operations we can measure its radius. However, this method raises serious concerns. We realize that atomic radius cannot be measured accurately, and it is due to two basic reasons. First, in 1926, Schrödinger proposed quantum wave mechanical model for atoms that reflected that there is no sharp boundary across atom. So we do not know actually where valence electrons lie. Second, the neighboring atoms can disturb the electronic charge density as their electrons can repel electrons of the understudy atom. Thus, atomic radius is not an accurate and absolute. So while studying this concept, keep in mind this critical idea. Now let me start it from core definition of ionic and covalent radii. Atomic radius is the distance between nucleus and the outermost valence shell. In the case of sodium atom, it is around 186 picometer. Picometer is the unit of. On the other hand, covalent radius is the half of the distance between two covalently bonded atoms in a molecule. In the case of hydrogen, H2, the bond length is 74.4 picometer and the half of it is 37.2 picometer. So the covalent radius of hydrogen is 37.2 picometer. Now let us develop on ionic radius. Ions are formed by either release or gain of electrons. First consider cation. It is formed by release of electrons. Generally, size of cation is smaller than its parent atom. To understand it, just consider sodium atom. Sodium has 11 protons and 11 electrons revolving in 3 shells. On removing one electron, it forms Na positive ion, that is cation, and this cation it has 11 proton and 10 electrons. One electron is removed from the valence shell, thus third shell is eliminated. On measuring the size of Na and Na positive, we get that Na size is 186 picometer, while the size of sodium cation is 99 picometer. Now there is a problem. Why is this happened? To understand this abnormality, consider the following demonstration. If we have a circular rope and there are two fixed masses circulating on the track, now consider if two persons are allowed to pull that circular towards themselves, they will definitely put a pressure. But consider one object is removed and now these two persons have to pull just single object. So what will be the results? Whether they can be able to pull more strongly? No doubt answer is yes. Two persons can put more force on the single object compared to one person on two objects or two person on two objects. The person in this case are proton, mean nuclear charge, while the objects are electrons. Thus nuclear charge is inversely proportional to ionic radius. That is why in case of sodium atom and sodium cation, sodium cation has smaller size. Now the similar case is for anionic radius, but the results are opposite. Size of anion is greater than its parent atom, and this is because of increase in number of electrons while the nuclear charge remains same. In the case of chlorine, chlorine atom has 17 protons and 17 electrons, while on receiving 1 electrons, number of electrons increases to 18, regardless of any change in nuclear charge. Now 17 proton cannot maintain balance force on 18 electrons. The size of chloride ion increases. In the comparison of atomic size of chlorine, that is around 102 picometer, now the ionic size becomes 181 picometer. Finally, we briefly discussed the trends of atomic and covalent radius in groups and periods of periodic table. Along periods from left to right, atomic size decreases. This is because number of shells remain same while the nuclear charge increases successively. On the other hand, in groups from top to bottom, number of shell increases and shielding effect becomes significant. These both trends can be observed along period 2 and 3 and in groups 1 and 2. Concisely, this lecture we answered a few important questions. First, what is atomic radius? Second, what is difference between ionic and covalent radii? Third, why size of cation is smaller than its parent atom? Fourth, why size of anion is greater than its parent atom? And finally, fifth, what are the trends of atomic radius in groups and periods of the periodic table? This is all for today. For further topics, visit our channel and subscribe this channel to keep yourself updated. Thank you.